Hi, this is MD Shabana Sultana, working as an associate professor in the Chevron Engineering College, Chevron. Today, I want to discuss about the superconductors. In that, what is superconductors? What are the types of superconductors, properties, and applications? What are superconductors means? A solid which offers no resistance to the passage of electricity through it is called superconductors. This phenomenon was discovered by the Dutch physicist Camerlin Onnes in the year 1911 when he was measuring the resistivity of mercury below 4.5 Kelvin. The niobium alloys were the earliest superconductors to be studied elaborately. Superconductivity can be understood with the help of quantum physics. Charged particles in the solids can travel only in a fixed direction or level. The electrons in a normal metallic conductors can collide with the metal atom and shift themselves from one level to another. But the electrons in the superconductors are prevented from such shifts by a unique quantum effect. These electrons are confined to their original level and therefore cannot collide with the atoms, and consequently it must travel endlessly along fixed direction. Under such a circumstances, they head in one direction and continue to carry the current endlessly. Therefore, superconductivity is exhibited by several metals, but only at its low temperatures. That means the temperature at which the normal metal passes into superconducting metal is called superconducting transition temperature or critical temperature. And it is denoted by the letter Tc. When the superconducting material it is cooled below its critical temperature, it becomes resistanceless and perfect diamond. The resistivity, the temperature behavior, that means the resistivity means the temperature behaviors for superconductivity and non-superconductivity material. It is differentiated by a graph by taking the resistance on the y-axis and temperature on the x-axis. See, the phenomenon in which the electrical resistivity of the material suddenly falls to zero or nearly to zero, where it is cooled to a very low temperature. That low temperature is known as superconductivity, and the material under such condition is called superconductors. In superconductors, if it is placed in the magnetic field in the critical temperature, all magnetic flux is expelled out. See, all the magnetic flux is expelled out, and its effect is called Misner effect. Perfect diamagnetism arises from special magnetic property of superconductors. If there is no magnetic field inside the superconductor, then relative permeability or diamagnetic constant mu r is equal to 0. Total magnetic induction B is equal to mu naught into H plus M. If magnetic induction B is equal to 0, then that means this value is 0. Then 0 is equal to mu naught into H plus M. Therefore, the value of M, which is known as the magnetic reverse magnetization, magnetization is equal to H minus H. Therefore, My minus H is equal to minus M minus 1. Coming to the types of superconductors. Superconductors are classified into two types based on their magnetic response. Type 1 superconductor, which is also known as soft superconductors, and type 2 superconductors, which otherwise known as hard superconductors. Coming to the first one, that is a type 1 superconductors. This type 1 superconductor these are the superconductors which becomes completely diamagnetic in superconducting stage, and it exhibits the Misner property, exhibit the Misner effect or Misner property, that is the expulsion of magnetic flux from the interior of a piece of superconducting material as the material undergo the transition to superconducting phase. And it shows the conductivity Cm, and it was first discovered and usually consists of pure metal and elemental metal, and it shows some conductivity at the room temperature, and it was discovered first, and it is usually consists of pure metals, because I already told you that this type 1 superconductor is usually consists of pure metals which are very soft, and elemental metals also. That's why this type 1 superconductor is known as soft superconductors. So here, if you take a graph by taking the critical field on the x-axis and magnetization on the y-axis, and when the magnetic field is increased or when the magnetic field is applied on the superconductors, it increases gradually. There, inverse magnetization is also increased linearly up to certain value, which is called critical field, and then it sharply falls to zero. And this type 1 superconductors, there's only one critical field and they exhibit complete viscous effect. Complete viscous effect. The value of the critical field are too low to have any useful magnetic applications. And therefore, two types of states, that is superconducting state and normal state, will be appear side by side. Coming to the type 2 superconductors, this type 2 superconductors is also known as hard superconductors because in this type 2 superconductors, a transition from the superconducting state and the normal state does not occur sharply as in the case of the type 1, but it occurs through a mixed region. Here, there is no mixed region, observe here. The superconducting state and the normal state, a transition occur suddenly. And here, the transition from superconducting state to the normal state, it does not occur sharply because it occurs through, but it occurs through a mixed region. And when the magnetic field is applied on the superconductor and increased gradually, there also the increased magnetization increases linearly up to certain value called first critical field. First critical field. From this, the penetration of magnetic field into the type 2 superconductor begins. Actually, in case of the type 1 superconductor, if we apply the magnetic field on the superconductor and increase gradually, the inverse magnetization, it also increases linearly up to this extent, which is known as the critical field, and thereafter it falls to zero. But here, as there is a mixed region between the superconducting state and the normal state, here only the first critical field it appears, and from this point, the penetration of the magnetic field into the type 2 superconductor begins. After another value of magnetic field called second critical field, which is also known as vortex region, the superconductivity disappears and material returns to the normal state. Most of these are developed from alloys, ceramics, transition metals, etc. And moreover, this type 2 superconductors, they do not exhibit the complete Mister effect as in the case of the type 1 superconductors. The transition between the superconducting and the normal state is not sharp. They have higher TCS, that is critical temperatures, than type 1 superconductors. Coming to the properties of the superconductors, superconducting materials are generally brittle in nature. This property limits their ability to be fabricated into useful forms such as wires. At room temperature, the resistivity of superconducting material is greater than other elements. A superconductor exhibits perfect diamagnetism. Because of diamagnetic nature, superconducting material sharply repel external magnets, which leads to the levitation effects. And it shows more resistance than other conductors at room temperature. Critical temperature of superconductor is low when a small amount of impurity is added. The superconducting state will be lost in the presence of magnetic field greater than a critical value, even at critical temperature. And in superconducting state, the material becomes diamagnetic. Thermoelectric effects of material disappear in the superconducting state. If a sufficiently strong magnetic field, if it is applied below critical temperature, which is known as superconducting transition temperature, its conducting property is destroyed. When a current is passed through the superconducting material, what will happen? The heating loss, and it becomes L2R becomes 0. That means the resistivity becomes 0. Coming to the applications of the superconductors, superconductors can be used to perform the logic and storage functions in the computer. Superchips may be made up of superconductors for computers can function 1,000 times faster than currently used silicon chips. Power can be transmitted through superconducting cables without loss, as there is no LR loss in superconductors, and is used to build experimental digital computers. And they are used in the MRI in the field of medicines, NMR missions, and mass spectrometers. And superconductors are used in the transformers, power storage devices, electric power transmission to transmit the power over long distance without resistive losses. They are used in electrical motors, magnetic levitation devices, etc. They can be used as a memory and storage devices in computers. And they can be used in wind turbines. Some superconductors are acts as excellent catalyst for industrial process. As the resistivity is zero, it combined with the high current densities make the superconductors useful for strong electromagnetics. They can be used for producing very strong magnetic field of about 50 Tesla, which is much larger than the field obtained from the electromagnet. Superconducting magnet capable of generating high fields with low power consumption are currently employed in scientific and research equipments. They are used for magnetic resonance imaging, that is MRI, in the medical field as the diagnostic tool. And the superconductor serves as gas sensors because the electrical resistivity sharply changes on contact with certain gases. Some superconductors functions as excellent catalyst for industrial chemical process. More powerful magnet can be made with the help of superconductors, which are likely to enhance the probability of laboratory nuclear fusion reactions. Superconducting magnets are employed for operating frictionless high-speed trains. Superconductors have very promising application as electronic filters. One possible use for these superconducting electronic filters would be in cellular telephone system, where it would allow more remote areas to be accessed. Superconducting material may be used in the manufacture of electrical generation and transformers in exceptionally small sizes, having efficiency of about 99.99% of yield. Coming to the last application of the superconductor, it is used for the computers. Super chips made up of superconductors can function 1,000 times faster than silicon chips. So this is about the superconductors, types of superconductors, properties, as well as the applications. Thank you.